Okay, so far we've seen how we can run tasks concurrently by using async and await. Anytime the runtime sees the await keyword, it'll kick off the current future that it sees and then look to see if there's any other asynchronous tasks to complete. But what if we have some big CPU bound task within a future? In that case, we'll be quote unquote stuck on one future until the next await keyword is hit. For example, we have this slow function here, and let's just pretend this is using a thread sleep, so it's not a future, but we're blocking the thread. This could be some heavy task to do, and so we'll go ahead and have two futures, and we'll kick them off using the select function, and this will switch between executing future A and future B only when, again, we have this await keyword. So what's going to happen here is we're going to run all these slow tasks from A, and then we're going to hit this sleep right here, and then do all these slow tasks from B, and then we're going to sleep again, and we're going to switch back to task A and print out we're finished. And we'll finish with future A, and then we'll finish with future B. So we'll go ahead and see this in action real quick. So as you can see, A started, A ran, then B started, B ran, A finished. The reason we don't see B finished in this one is because select again is erasing a function here. So as soon as A finishes, it's going to go ahead and drop B. We can mitigate this by, I refactored it real quick, by putting in these TRPL sleep functions, and this is different from thread sleep. This is a future sleep, so it doesn't block the thread, but instead looks for other async work to do for 1 millisecond. So I'll go ahead and run this, and we'll see that this actually gets interleaved now. So as we can see, A started, and then we ran a single blocking task, slow A. B started, blocking task, switch, 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 until A finishes. One important tidbit here is that even though we're sleeping for 1 millisecond here, we're actually guaranteed to block for longer because all of our synchronous work takes longer than a second. As you can see, all these slow tasks here take longer than a millisecond. And we give our runtime, we switch our runtime to run these slow tasks, and there's no opportunity to switch back to the sleeping future until a slow task is done, right? Because this is a CPU bound task. But nevertheless, this gives the runtime, as we've seen, the ability to switch from A to B without completely blocking B. In these in-between times here, we're able to switch. Whether this is a big deal or not really depends on your use case. If A and B were two user requests coming into a single threaded server at one time, and let's say it takes, I'll just write down here, we'll say we have user A request, and this takes 1 second to complete, and we have a user B task that takes 1/10 of a second to complete, and they come into the server at the same time. We probably don't want user B waiting a full 1.1 seconds to complete if it's only a really small task to complete. If we ran these concurrently, then user B will take under a second and user A will take just a little bit over a second, like 1.05, something like that. Whether this is a big deal or not, again, depends on your use case. We can do better though. Instead of doing this weird kind of hacky sleep thing with the TRPL crate, TRPL actually has this yield now future, which basically acts like a super tiny sleep. And its purpose is to just check to see if there's any other futures that are waiting for work to be done, and switches to those until the next await keyword is found in that future, right? So it's going to behave just like how we wrote, except we don't have these hacky 1 millisecond sleeps, right? So I'll go ahead and just prove my point here. As we can see, we interleave between the tasks, and this is a much cleaner way to split up synchronous work, right? Let's move on to these asynchronous abstractions. We've actually learned enough at this point to build our own future. We're going to build a timeout future. This function will take in a future and a duration, and if our future takes longer than the given duration, then we'll return a result type of error. Otherwise, we'll return okay with that future's type. So we'll begin. We'll declare our asynchronous function here. We're saying that this function returns a future, and it's going to be called timeout. And we're also going to define the generic type f, which is going to be a future. And our input parameters are going to be future to try, which is going to be type f. And then our maximum time that this future can run for, which is going to be duration. And our result, or our return value, is going to be a result. And this is syntax we haven't seen before, but it's kind of self-explanatory. So again, future is a trait, right? And this trait defines a type on it of output. And that output type just says, okay, like, what is our output type? It's basically another generic within this trait, right? That gets defined as we implement the trait. So we have the future here, the future generic, and then we're going to define, or we're going to specify that it's going to be the output type. And then if we fail, our error is going to have the max time duration on it. And we're going to basically race between our future to try and max time. And we can do that with the select function off of the TRPL crate. So we're going to match TRPL select future to try, and that's going to kick off that future. And then we're also at the same time going to sleep for the maximum allotted time that we have said. And since this is within an async block, we can use await. And then again, this select is going to return an either enum here, and that's going to have left or right, whether the left finishes first or the right finishes first. So we're going to say either left, and we're going to destructure our output from the future. This is saying that our future to try finishes before our max time. And all we're going to do here is return it with the OK variant. Otherwise, if we get the right, we don't really care about the output from sleep. We're going to return an error with the max time. I also real quick just brought the either enumerable into scope. I had and just cleaned up our code real quick, so I got rid of our previous example with the slow synchronous blocking futures, and now I've redefined slow to be just this good old future here that does a long sleep. And note that this is not blocking. Otherwise, our timeout might not work, because select wouldn't be able to switch between this blocked future and the sleep. So I'll go ahead and run this real quick. Again, we're seeing if slow runs quicker than 2 seconds. If it doesn't, we're going to print out error, failed after 2 seconds. So go ahead and cargo run. Waits 2 seconds, and it failed. We officially have a good timeout function. Now, if this was thread sleep, we're not going to run into this, or we may or may not. Actually, we won't, because we're not going to see our error message, because our select is going to run these in order, these futures in order. So It's going to first kick off our future to try, which is blocked. It's a blocking future. And then it's not going to have a chance to run this sleep future until we're actually finished with our future to try, which is our slow future. So I'll go ahead and run this. As you can see, we're waiting 5 seconds. And it actually finishes. So that's the importance of having either yield now or some other awaitable future within CPU heavy parts of our async code, so that our async runtime has the ability to switch between futures, such as in this case right here. We can also use this pattern of using futures to build other futures, using quote-unquote future primitives such as await and async, and then select and join to create things like streams or handling multiple network requests at the same time. But that's it for this video. I'll see you in the next one. I'm going to keep off the exercises for now.